that we had from last time. If they have the same direction, if A and B have the same direction, you get the product of the magnitudes. Opposite direction, the opposite of the product of the magnitudes. And then if A has a component in the same direction of B, you get a positive value, but less than, right, according to how much of this one is in the direction of this one. And then negative opposite. Okay? So the value of the product, the dot product is the product of the vector's magnitudes, but only as much as the vectors are in the same direction. That's kind of the conceptual idea behind the dot product. The product of the magnitudes, but only as much as they're in the same direction. If they're not at all in the same direction, 0, right? Orthogonal, 0. Okay, so let's do some work. So we spent a whole week, we haven't done work yet in this class. You know that? Get it? I got jokes today. I got jokes. All right, so work is defined as the total amount of force applied over a distance. Okay, so we can investigate the amount of work to move an object, scalar quantity, by observing the force applied and the displacement of the object. So if I apply a force to this chair for a certain displacement, right? Those are both vectors, right? There's the force I'm pushing on the chair, and then there's the displacement of the chair. So based on those two vectors, we should be able to figure out what the work that I did on the chair was. So here's a similar example. So you got a girl pulling a wagon. Okay, and she's going to use a force of 56 newtons, pulling up at this angle here, 39 degrees. And she's going to do that for 8.1 meters, something like 25 feet, okay? She's going to pull with 56 newtons and go a distance of 8.1 meters. So those are those two, here's the two vectors in that situation. Now the 56 and the 8.1, those are just the magnitudes, right? Those aren't the vectors. The vector also has the direction. So if I'm labeling the 56 and the 8.1, I'm going to label those with magnitude bars, right? So we want to know how much work she did. So let's first practice, see how we're doing on just understanding vectors. Can you write both those vectors in component form? Can you write F as components and D as components? Can you do that? That would be a review or from last week. So let's see. So tell me your name in the plaid shirts. I got to learn your names.
Chandler.
Chandler. So take your pick. Can you write either F, vectors F or D in component form? You can pick.
So D would just be 8.10.
He's offering up 8.10. 8.1 comma 0. Agree with that? I see some nods. Yes. And then what about F? So then the F is a little bit trickier. Any volunteer? What would be the components of F? Tell me your name.
Brian.
Brian.
56, 39.
So that would be the polar form. So if you're reporting the magnitude and the direction, you'd be reporting polar form. But the component form would be like, what's the x and the y component? You want to try again? How would you get the x component of that and the y component of that? Okay, sure. Tell me your name.
Giorgio.
Giorgio.
It would be 6 sine 39 and 6 cosine 39.
Which would be which? What would be the x component?
The x would be the cosine.
Okay, so 56 cosine 39 and 56 sine 39. So there's the F component, or the components for F form, and then the component form for D, 8.10. So what is just the generic formula for work? Did you guys learn that in physics? Just how do you get, yeah, regardless of vectors, it's just, the basic formula is force times distance.
Is it the force and the direction of the distance? So it would only be the x1?
Right, so what component of the force contributes to the work? Do both components contribute to the work done? I heard yes, and I heard only the x component contributes. How does the y component contribute to moving this thing horizontally? Does it? It would just be like trying to pull it off the ground, right? So the y component just tries to pull it straight up, and it doesn't contribute to the work. So what contributes to the work? Just the x component, right? So our force, so if we're just forgetting about vectors, the force applied to the wagon is? The 56 cosine 39, and the distance that she walked? 8.1, so force times distance, right? So force times distance, 56 cosine 39 times 8.1. You get 352.5 joules of work, or Newton meters is joules. But so notice something, right? So the work done was the product of the magnitudes of the two vectors. But was it the product of the two vectors? What was it? But only what? Only as much of the force that was in what? Same direction as that. Sound familiar?
Yeah.
What is that? Isn't this dot product, right? So we're taking as much of the force as is in the horizontal direction. That's exactly what dot product is, right? That's what we said, right? So let's show that. So let's do the dot product. Or so, because that's where the cosine comes in. Because cosine then gives us the amount of f that's in the direction of d, right? So this is the alternate formula for the cosine, so for the dot product. So far, the dot product, you've been multiplying the like components and adding up, right? So here's an alternate way to do the dot product. And it matches a lot more this whole meaning that we've been emphasizing, right? That you just take the part of the one in the direction of the other. That's what f cosine is. So go back and do it the old way, right? Let's do it the old way, where you multiply components and add. What will happen? Look, if you multiply components, so multiply the x components, multiply the y components and add, and what do you get? Same thing, right? You get the 56 cosine 39 times the 8.1 plus 0. Okay, so the moral of the story here is there are two ways to compute the dot product. Don't forget that. They compute the exact same value. There's only one dot product, but there are two ways to get it. The old way was multiply the components and add, and now our new way is, which goes along with the meaning, right? Goes along with the meaning. Magnitude of the first times magnitude of the second times cosine of the angle between them. Which gives us this whole thing of how much of the one in the direction of the other. Oops. So whenever you have to find the dot product, choose the easier, right? Don't do more work than you have to do. If it's easier, if you have the components and it's easier to multiply components and add, then do that. Or if you're given the angle and you have the magnitudes or something close to that, then use the other way. They both compute the dot product, which is the same value either way. Okay, so here's another work problem. Any questions on this work problem or the setup here? All right, here's another work problem. How much work is done to push a box from point -1, -2, 1, 0 up the ramp to point P, which is shown there at the top of the ramp, if the force applied is 8, -15, 0. So here's -2, 1, 0 is about here. Would you agree? Cool. All right, and so then what we've got, so this is the displacement vector. I'll try that one more time. Slightly better, okay. That's my displacement vector. And then my force vector is what? 8, -15. So do something like this. Oh no, not like that. This. I'm gonna try. Right, it's in the positive x direction, but the negative y direction. And then horizontal, right? No z component means that force is horizontal. Okay, so I'm going to have to, maybe I could resketch those vectors tail to tail. And I'm going to have to find the angle between those, right? And then I can get the dot product. Is that right? Is that what I want to do? So to get the work, I'm going to do magnitude of f, magnitude of d, cosine theta. What do we think? Giorgio says no. You say no. Tell me your name again.
Lucas?
Lucas says no. Why?
Because you have to find the angle first.
Okay.
If you just do normal dot product, it'd be a lot easier, a lot faster.
And when you say normal dot product, what do you mean?
So like you would just do what is it? The components have each other.
Right. Yeah. So you see, this is awful, right? So now we're in R3, and I've got these two angles that are like, or these two vectors that are, you know, who knows what that angle is, right? So instead, what do we say? There are two ways to compute the dot product. The work is f dot d. So pick the way of computing f dot d that's the most efficient, which is, what is f? Right, multiplying component. Is that what you're going to say, Giorgio? Good. F dot. And what is d? Nope. That's not the displacement vector. What's the displacement vector? 5. -7, 2. Does everyone see that that's the displacement vector? Final minus initial, final point minus initial point gives the vector between the two. So what do we get?
40 plus 105 plus 0. So 145.
And since it's feet and pounds, it'd be foot pounds. So the English units for work are foot pounds. Which is the exact same number I would have gotten if somehow I had the angle and did the magnitudes and did this formula. Okay, does it make sense? Choose the most efficient way of computing the dot product. Okay, well, now that being said, what about finding the angle? So let's pretend we've got these two vectors and I want to find the angle between them. Any ideas? How could I find the angle between them? Giorgio thinks he knows. Kyle, you got an idea?
Can you do the trig inverse?
Okay, can you be more specific? Like, can you talk it out a little bit more? What do you mean?
Could you do the trig inverse of maybe vector f over vector d? Like that? Or
Okay, so something to do with trig inverse. Tell me your name again.
I'm Jacob.
Jacob.
Well, if you were given the magnitude of f and d, wouldn't you be able to multiply? No.
What do you mean if you were given them?
No, I was thinking that we could solve for theta and then do the inverse like Kyle was saying, but well, if you were to find the angle though, like say of vector e, and you could draw the right triangle and then like do all the tricks.
Oh, I liked your first idea better.
Oh, you did?
Yeah, sure. Okay, but there's more than just, you get to take the inverse function. So we gotta, what's the whole process here? So tell me your name at the board. Yeah, Philip. Do you know how you find the angle? Look, we've got the dot product as 145, right? We're trying to find the angle. So what does 145 equal?
Oh,
It's
so
not
you
equal to 45.
would you divide the S over
Mm-hmm.
45 and then take the inverse?
Right. So can we find the magnitude of f?
Yes.
Can we find the magnitude of d? Sure. So this 145 equals the magnitude of f times the magnitude of d, cosine theta. These are both attainable, right? We could find both of these. So what would we do? Cosine theta equals 145 over, see, magnitude of f. Can we do that here? 225 plus 64, is that right? It's 225 plus 64, 289? Check my math. Is it 289? That's the magnitude of f. Magnitude of d, 25, 49, and 4. 74, 78? Check my math. I'm doing it in my head. This is the magnitude of d. This is the magnitude of f. So let's put that in. 145 over radical 289 and also over radical 78. Let's get a number for that. As soon as you get it, shout it out. As soon as you get that, shout it out. Let's just do this. Let's make sure we all agree on this ratio first.
This is just supposed to after.
0.97.
0.97. Is that what you got too?
Yeah.
0.97?
Yeah, cosine theta equals 4.
Is everyone able to get 0.97? I've got 2 confirmed with that. All right, so then theta is?
15.0.
Oh, that sounds like radians. If it's 0.97, it's going to be almost what? If cosines, oh no, sorry. I was on the wrong side. Okay, so cosine 0.97. So we want the arc cosine. Okay. 14.1? Someone else get that? Is that what you got, Cutter? Sorry.
I got 15.0, but I used the full number, so yeah.
I got 15.
15.0?
Yeah.
So it depends if you round this first or not. So probably you were using the non-rounded version.
Yeah, I did.
Yeah, that's better. So this is 0.97 dot dot dot, whatever that is. If you use that, you get the 15.0. So given any two vectors, the dot product, now knowing the two formulas for the dot product, allows us to solve for the angle between the vectors. So you'll have to do the dot product the old way, set that equal to the dot product the new way, divide by the product of the magnitudes, inverse cosine. Does it make sense? Any questions on the word problem or finding the angle between two vectors? Are we good to go on? Please. Okay, you guys, could you whisper? This is the force. That's the displacement vector. So this is the starting point and the ending point. We need to make a displacement vector out of that. So it's final mass initial. Other questions? Okay, moving on. So there's another thing that's important here that's called projections. There's something called the scalar projection of one vector onto another. So this is a scalar projection. Okay, so we're doing B onto A, the scalar projection of B onto A. And so what is that? That's the length. This is a scalar. So since it's the scalar projection, it's the length. It's the length that gets projected onto A if you project V onto A, meaning like if you took a light above B and you shined it down perpendicular to A, it would be the shadow of B, right? Or it's this whole idea of like how much of B is in the direction of A, like that's what we've been talking about, right? How much of B is in the direction of A? That's the scalar projection. Does someone have a question? Yeah.
So it's kind of how much of one overlaps the other, kind of?
Kind of like if you were to flatten B right onto A, then what would you have? What would be left? It'd be that length, right? Okay, yeah. Okay, so how would you get that little length right there? So what would be, based on, before we even started this course, how would you get that length? That length right there?
Solving for that length.
Tangent? So tangent would be, we would use tangent, who said that? So we would use tangent if we knew this length right here, which we don't. So instead, which one do we know?
Cosine.
Yeah, so we know B, we know the hypotenuse. So what is that length again?
Call it C, I guess.
Okay, and so C would equal what?
B cosine.
All right, not quite. What cosine theta? B is a vector, right? B is a vector. Magnitude of B times cosine theta would give you this adjacent side of that triangle, right? Okay, but that kind of looks like something. What does that look like? A little almost, that's almost what? Dot product, right? What's the dot product? A dot B is? Magnitude of A, magnitude of B. So how can I rewrite magnitude of B cosine theta in a different way using dot product? It would be, so this is what I'm asking about, right? So what does that equal? No, just do algebra. It's just algebra. What would you do to isolate this, right? You're just doing algebra. The dot product divided by magnitude of A. Do you see it? What's the advantage to finding the scalar projection this way? Why would this be advantageous? Or in what case would it be advantageous? Right, when you don't have the angle. You see that? So you could find that length without the angle. Do you see that? If you could use the component version of the dot product, divide by the magnitude of A. You never have to know the angle, and you can get that length. Make sense? Okay, now the vector projection is that orange vector now. So I want to write that orange vector in terms of vectors A and B. So we have all the tools to do that. You have everything you need to do that. You just have to remember what we've done before that gets us that orange vector. That's called the vector projection of B into A. So this is just the magnitude of that orange vector, right? That's the scalar projection. What about the vector itself? What direction is it in? A. So look, you want a vector that's in the direction of A and has magnitude of that. Can you do it? This is review. I need a vector in the direction of A that has this magnitude. Who remembers? See if you can. So everyone think about it yourself. See if you can do it. You need a vector in the direction of A that has this magnitude right here. Can you remember? Let's see, somebody new. Somebody new. Is it Raj? Raj, is that your name? Any ideas to write how I'm going to write this orange vector right here? Yeah, Jacob. Is that right? No. Lucas. Who's Jacob? Over here. Okay, sorry.
Wouldn't you just multiply the reciprocal of the scalar projection to the components of A? Because you'd be dividing by the scalar projection, which would make the scalar. You find the magnitude of the components, and then you make it to unit.
Make what into a unit?
Unit vector of A.
Okay.
And then once you have the unit vector of A, then you multiply it by the scalar projection.
Okay, good. So we're going to start by, good job. Way to think it and talk it out. So we're going to start with, so now let's do the math. So tell me what first then?
So
Lucas?
you find the unit vector of A,
Okay.
then you multiply.
Which is what? How would I write down the unit vector in the direction of A?
So it would be the components divided by the magnitude of A, of vector A.
We don't have the components, right? So
You could just do A divided by the magnitude of A, right? What if that is the same thing? If we don't have components.
let's go back to Lucas. What do you think, Lucas?
Okay, that makes sense.
What is that? So tell me what that is.
So vector A divided by the magnitude of vector A
Gives
gives the unit vector of A.
in the direction of A. Yeah, the unit, right, okay. So now that's in the direction of A and has length or magnitude, what? 1. And now what do we want to do? We want to scale it. How much do we want to scale it by? The scalar projection, right? So we want it to have this length, right? So we want to take the unit vector in the direction of A, and we want it to have that length. So we scale it up by that much. Should make sense. If you remember that process from Thursday, right? That we did that on Thursday. So now we can simplify this. I can gather those magnitudes of A and square it on the bottom. So we got A dot B over magnitude of A squared. That's the scalar times vector A. And so then we get the vector projection. So this whole thing is a scalar. And it's how much you would scale A by to get the vector that's the vector projection of B onto A.
If you put the squared inside the magnitude bars, would it be wrong? Or is it the same
Well,
thing?
that doesn't make sense. So you can't square a vector. That doesn't make sense,
Okay.
right? You square a number, you square a scalar. You can't square. I mean, you're saying A times A, but we have 3 kinds of multiplication, right? Or we have 2 so far, but this doesn't specify what kind of multiplication you're doing.
Okay.
Question?
The dot product of A and B divided by the magnitude of A is the length of that orange vector.
The length, that's the scalar projection, right?
Okay. And then the projected projection after you work out all that math will give you what?
The orange vector.
Orange vector.
This is the orange vector right here. It's the vector projection. So we got the unit vector in the direction of A. Say that's this right here, okay? Let's say that's the unit vector in the direction of A. We scaled it by this much, which is the vector, this length right here. So we get the orange vector. That's it. Okay, so just, what would, let's just mix it up here. How would you draw the vector and the scalar projection of C onto D? C onto D. So the vectors look like this. I've got C onto D. So to do that, first you'd have to kind of extend the line of vector D. And once you extend the line, then so which way is that projection, the vector projection, going to point? Do you see which way it will point? Was it? In the opposite direction of? D. Well, let's stick with orange here. So that would be the vector projection of C onto D. Now what's going to happen in this case? When I do the scalar projection, what am I going to get? Do you notice what I'm going to get? Negative, okay? So that scalar projection, just the length of this, also is signed, S-I-G-N, signed, meaning if C and D are in opposite directions or have components in opposite directions, then your scalar projection will be a negative number because that dot product is negative. Do you see that? So it's more than just the length, it's the signed length. It means either positive if they have a component in the same direction, or the scalar projection will be negative if they have components in opposite directions, like this example. So here the scalar projection will be negative. And that orange vector will be the vector projection. Okay, questions on that? Okay, so part of your homework will be, there'll be the homework problems from the book, and then I have two more kind of a little more challenging problems, and the big hint is that you're gonna apply scalar and vector projection to do those a little bit more challenging problems that I gave you, okay? So that's your hint. Questions on that?
I do have a question. The scalar projection and the vector projection are the same, it's just different ways of finding it?
Mm-mm. What's different about their names? What's different about their names?
One shows direction.
No. Jake.
It's a scalar or vector.
Right. So what's the scalar projection? What is it?
Scalar is like how much it's multiplied by, correct? So the scalar projection, is that in the y direction? Because so B is flattened, and the scalar projection, is that the opposite
So here's
side
the
of
key.
the angle?
No, here's the key. It's a scalar. That's the key to it. What is a scalar?
It's a value multiplied.
Just a value. It's a number, right? So when you project B onto A, what value is in question here?
The value B in terms of that.
Well, it could be. I guess that was my question. Is it the side? Okay, so it's the length. But
It's the
not
length
the side
of
opposite.
whatever. When B is projected onto A, it's that length.
Mhm.
It's that value. It's that number.
Okay.
So then what's the vector projection?
The vector is the vector of the length.
It's the vector that was projected of B. When you project B onto A, it's the resulting vector that you get.
Okay.
So how does the scalar projection relate to the vector projection?
So is the scalar projection the magnitude, and the vector projection is
The scalar projection is the magnitude of what?
of B onto A. B projected onto A.
Which is called what?
Scalar.
No.
I don't know what you're.
The scalar projection is the magnitude of what vector?
Oh, okay, the vector projection.
The vector projection, right?
Okay.
So this is just the magnitude of this.
Okay.
So we started looking at the length of that, and then we said, okay, what's the vector of that? So that's just the magnitude of that.
Okay.
Question in the back.
So with vector projection, when you multiply both of them together, it's just like, so scalar is flexible of like the yellow on the top, and you multiply by the unit vector, like the direction. So like the scalar is just the vector is the magnitude of direction. So it gives you vectors.
Maybe. I wasn't really following what you're saying. So try me again. Let's go back. So what's the scalar projection? It's when you project B onto A, it's the length that you get. Do you see that? See what I'm showing there? That's the scalar projection. Okay? Okay, you guys gotta be quiet so I can hear him. If you're working on the math, that's fine, just whisper. Go ahead. Nice and loud. I can't hear you, nice and loud.
So the length of the top like a direction.
Right, length is just a scalar. That's why it's called the scalar projection, because it's just, scalars are numbers, right, that don't have direction. So it's just that length.
And then you multiply it by the unit vector.
If you multiply that length times the unit vector in direction of A, then you get the vector projection. That's right. That's right. If you multiply, so now we come along, multiply that scalar projection times the unit vector in the direction of A, and you get that orange vector, which is called the vector projection. Therefore, the scalar projection is the magnitude of the vector projection. It's the length of that vector. Better? Go back and watch the video. So yeah, you can go back and review the video and pause it and keep thinking about it. So this should be what we said. Don't write this down. I'm about to take it off. But this is exactly what we said. Oh, so the scalar projection often has this notation. Comp, meaning the component of B onto A. And that's the scalar projection. Vector projection, PROJ, or for projection of B onto A. And these should be exactly the formulas we came up with. Okay. Okay, so scalar multiplication multiplies what by what and results in a what? Scalar multiplication multiplies a scalar by a vector and gives a third, it gives a second vector, right? A scaled version. That's why it's called a scalar, because it's scaling the vector. Like a magnified or shrunken version of that vector, but then there's also, if your scalar is negative, what does it do? Flips the direction, right? So that's the first kind of multiplication. Second kind of multiplication is the dot product. And what does that multiply? It multiplies a vector by a vector and gives a scalar. Gives a number, right? And that number, one more time, means that number is essentially product of the magnitudes, but as much as in the same direction, right? As much as the one direction is in the one vector is in the direction of the other, you get that kind of portion of the product of the magnitudes. That's where the cosine comes in, right? Cosine. So there's a third kind. There's a third kind of multiplication, and it's called the cross product. The The cross product is still a third way to multiply vectors. You multiply a vector by another vector, and you get a third vector. So basically, all of them are cross negative 3, 0, 0. And then the first vector starts at 3, 0, 0 and then winds its way around what? Which quadrants? You see, this is the only vector that changes, right? And so as you progress through these 7, it winds around like this. What quadrants are those? 1 and 2, right? So what happens when the vectors are parallel? What do we see? Which cases are the vectors parallel?
The first one and the last.
First and last, right? So the first and last are parallel, and what happens? Yeah, and so we never really mentioned this, but this, when you have all components are 0, that's called the 0 vector. And it has 0 magnitude, and it doesn't have a direction because it's essentially a point, right? But not a point, it's not a location, it's just, there's like no change to any component, right? So there's no direction to it, and there's no magnitude. So how does that compare to the dot product? What happened when you were parallel with the dot product? Maximum, right? So it's either maximum positive or maximum negative. So here it's like the inverse situation when you're parallel. And so what's happening here, as we increase this angle of that first vector and start increasing it, what happens to the cross product? And when is it maximum? So you get, for cross product, you get maximum when the original vectors are orthogonal. So it's like the inverse situation of the dot product in a way. And then as the angle gets more and more smaller and smaller, what happens to the cross product? Decreases again until 0. Okay, so forgetting about direction and just thinking about magnitude, how could we qualify what the magnitude of the cross product is? The magnitude of the cross product is, and notice, what's the value here? What's the value of, what's the magnitude of the cross product, max? What did that have to do with the original 2 vectors? How does that number compare to the, just no direction here, no vectors, just numbers, scalars. How does that come from these two? The multiply, it's the product of the magnitudes again, right? So this is the product of the magnitudes again. The magnitude of this is 3, magnitude of this is 3, and our cross product is product of the magnitude. But now it's when what? When they're perpendicular. Again, the exact inverse situation of dot product. So the magnitude of the cross product is also the product of the magnitudes, but as much as what? Yeah, as much as the vectors are perpendicular. The least they are perpendicular to one another. So more and more in the opposite direction brings the magnitude down until it's 0 when they're in opposite directions. Or bring those vectors closer to the same direction. Again, the magnitude comes down until they're in the same direction and the magnitude of the cross product is 0. So it's the The magnitude of the cross product is very similar to the dot product. It's just the inverse situation. The product of the magnitudes only as much as they're orthogonal. And if they're not orthogonal at all, then your cross product magnitude is 0. Now, what about the direction of the cross product? So the direction of the cross product, what do you notice about all these vectors? These cross product vectors in the positive z direction. Okay, and how does that compare to the original two vectors? Yep, and if they're in the xy plane, then that resulting vector is always what? How does it compare to those original two vectors? Isn't it perpendicular to all those original two? The original two are in the xy plane. And this cross product we're getting is orthogonal to the xy plane. And therefore it's orthogonal to the two vectors we started with. But the question is which way, because there's actually two directions that are orthogonal to the xy plane. What's the other direction? Down, right? So the way that you know whether it's, so the direction of the cross product is orthogonal to both of the two vectors that you started with. And the way you know which way that is, because there's two choices, is again by the right-hand rule. So what you want to do is you want to take your right hand, so you can do the, let's see here over. That doesn't work. Okay, so so if you use your index finger to point in the direction of the first vector, and your third finger to point in the direction of the second vector, and get that lined up like that, then your thumb will tell you the direction of the cross product. Does it work? So index finger points which way?
First.
No, did I blow that?
For y.
0, 3, 0. No, that's right. 0, 3, 0 is this one here. So there you're pointing to the right, right? And then negative 3, 0, 0 is your third finger that points back into the board, right? And so which way is the cross product then is up the direction of your thumb. Make sense?
Yes.
Oh, you're right. Sorry. Explain what it is.
Let's do another example down below.
How does this work?
Let's find one here. Let's see. How about no? Okay, here's one. Let's do this one right here. Negative 3, 4, 0. Let's sketch that. Negative 3, 4, 0. It's something like that. And then 0, 0, 1 is this right here. First of all, what do you notice about those two vectors? Negative 3, 4, 0. And 0, 0, 1. Are those orthogonal?
Yeah.
So what about the magnitude of the cross product? If these two are orthogonal, then the magnitude of the cross product will be? The inverse situation of the dot product, right? So this, then therefore, since these are orthogonal, the magnitude will be the product of the magnitudes, right? Because we have these are orthogonal. So what is that? Magnitude of this one is 1, Magnitude of this one is 5, right? Square root of 9 plus 16, square root. So the magnitude of the cross product will be 5. And now in what direction? We can use the right-hand rule to figure out what direction. So we're going to point our index finger in the direction of the first vector, and then our third finger in the direction of the second, 0, 0, 1. So you got to orient your hand so that happens, okay? So so negative 3, 4, 0 is this way, and so then in order to get it to be up, it'd be like this. So which way does the cross product point? Into which quadrant? First quadrant. Do you see that? Get your index finger in this direction. Get your third finger in that direction. So there were two possibilities. The cross product could have pointed in the first quadrant or the third. But according to the right-hand rule, it has to be in the first. I know there's a funny joke about road rage in here somewhere. So it's this way. And what's the magnitude of it? 5. So it's going to be into the first quadrant such that it's orthogonal to this vector and also orthogonal, it's in the xy plane, so it's orthogonal to 0, 1, 0, and the magnitude is 5. Question, please.
You should explain how you got the 5 one more time.
Okay, so the 5 came from the fact in those first 7 examples, remember this one here? We looked at this one. And we got 0, 3, 0, cross, negative 3, 0, 0. And since those were orthogonal to each other, the magnitude of the cross product ended up being the product of the magnitudes in the case where your original vectors were orthogonal. What about when you're doing the dot product and the vectors are orthogonal? What do you get? 0. But in this case, we got magnitude of 9. We got the best case scenario is when they're orthogonal. In the dot product, the worst case scenario is when they're orthogonal. Okay, so going back to this one.
And then to find the coordinates, would you?
Components?
Yes.
We're about to do that.
Okay.
We're about to do that.
Sorry.
No problem. That's the right question. All right, but just questions on the conclusions we've made so far. If the original two vectors are orthogonal, then the magnitude of the cross product is the product of the magnitudes. So that's why we did 5 times 1. And we said it's going to be magnitude of 5. And then we used the right-hand rule to figure out there were two possibilities for its direction, orthogonal to this plane here. It could have been one possibility is into the first quadrant, the other possibility is into the third quadrant. But by the right-hand rule, index finger, third finger, then your thumb tells you. So index finger, third finger. Be nice. This is math. Right? And your thumb points in the direction. I know there's some great jokes in there somewhere, right? With this right-hand rule thing. Okay. So now any questions about that? So now I want to show you the algorithm. Given the first two vectors, how do you actually get the components of this? Okay, and so there's an algorithm for that, and here's how it goes. So what you're going to do is we're going to find, what are we finding? Negative 3, 4, 0, cross 0, 0, 1. And to do that, you're going to set up a matrix, a 3 by 3 matrix. The first row in the matrix are your I, j, and k vectors. Second row is your first vector. Third row is your second vector. So it's a 3 by 3 matrix with I, j, and k. And then you write down the first vector cross the second vector. And what you're going to do is we're going to find the determinant of that matrix. So we want the determinant of that matrix. Anyway, there's multiple ways to find the determinant. And so any way that you can want to find the determinant will get you the right answer, okay? So the way that I suggest is we're going to write down the first two columns again over here to the right. So I, -3, 0. And J, 4, 0. All right, and then what you do to find the determinant is you're going to multiply down to the right. There are 3 diagonals. Yeah, I'll do. I still want it to be light though, so let's try this. Does this show up? Okay, so the 3 diagonals, I, 4, 1, J, 0, 0, and K, -3, 0. Do you see those 3 diagonals down to the right? So we're going to multiply down those diagonals and then add. So it's going to be 4I is the first diagonal plus 0J plus 0K. Did you follow that much? And now we're going to do the down and to the left. There's 3 diagonals down and to the left. Starting here with the K. There's one this way. And then there's one here. And then there's one here. And we're going to multiply and subtract those. So what's the first one? Minus 0K. Minus 0I. Lots of zeros in this one. Minus -3J. So it becomes plus. Minus -3. And then you're going to combine your like components, and that gives you the cross product. So what's our cross product? 4I. Does that vector confirm the conclusions we made about the cross product before? So what were the conclusions we made? Magnitude 5. Does it have magnitude 5? Check. And then does it point into the first quadrant? Yes, check. Direction, first quadrant. So there's two aspects to this. There's kind of the meaning of the cross product, okay? And so the meaning of the cross product, now you have to talk about 2 things because the cross product is a vector, not just a scalar, right? So you have to talk about its direction and its magnitude. So when you talk about the magnitude of the cross product, this is where it has this kind of this inverse relationship to the dot product, right? When they're parallel with the cross product, you get a magnitude of what? When the original vectors are parallel, the magnitude of the cross product is 0. 0, right? That's the maximum situation in the dot product. It's the 0 situation in the cross product. As the angle gets closer and closer to 90 degrees, it increases. Your cross product gets better, right? Dot product gets worse, but cross product gets better until you hit 90 degrees. And then what's the magnitude of the cross product when those vectors are 90 degrees? Max, which equals? Product of the magnitudes when they're orthogonal. The direction of your cross product is according to right-hand rule. Index finger in the direction of the first vector. So orient your hand so your index finger points in the direction of the first vector, your third finger in the direction of the second vector, then your thumb tells you the direction of the cross product. So should we try? Let's try one more from the sheet here, maybe with less zeros. Try something else here. How about? Oh, you want to do bottom left? Sure. So let's do bottom left. Sketch 0, 3, 4. And then 0, -4, 3.
Is that right?
Your first.
The first one's wrong.
Yeah.
I did 3, 4, 0, didn't I? I'm not very good at math. 1, 2, 3, 1, 2, 3. So these are both in the YZ plane. Are these two vectors orthogonal?
Yes, they are.
They're both in the YZ plane, and how do you know they're orthogonal for sure? Dot product is 0. They're both in the YZ plane, so they're both in the plane of the screen, or both in the plane of your page. And since their dot product is 0, we're orthogonal, okay? What's the magnitude of the cross product going to be? The magnitude of the cross going to be? Not 5. Was it? What will it be? 25, right? Magnitude of the first is? 5. Second is? They're orthogonal, therefore, product of the magnitude is 25. And now, in what direction? So it's either going to be in one of two directions, either in the, what, positive x direction or negative x direction. So, right hand rule, right? Index finger points 0, 3, 4. Their finger points 0, 4, -3. Therefore, you guys are saying positive?
Yes.
So, because you know the magnitude and the direction, you can write down the answer before we do the algorithm. What's the answer going to be? 25. We know it's in the positive x direction. We know its magnitude is 25. That vector is 25, 0, 0. So now we'll do the algorithm and confirm that. So what we're expecting is, right? So that I can't even fit that on the screen. Zero, 3, 4, 0, -4, 3. So if you want to just go, you're off to the races if you remember what to do, or you can watch me. I won't talk, I'll just do it, or you can just try to do it yourself. Tell me, is this right? Is this what it was?
0. No.
So
it's the
4, so
3
that
and
-4 should be a +4, and then the +4 should be -4.
Negative, positive here?
Yeah.
Like this?
Yeah, just like that.
Okay.
Wait a
I'll
minute.
just look at
3, 4. So it should be -4.
-4, 3. Thank you. Okay, so I got a quiz. We got to take one question off the quiz canvas. So in the meantime, while I'm doing that, I want you to figure out with the right-hand rule, what's the direction of negative I cross negative j? Negative I cross negative j. Talk about that. So you're doing negative I cross negative j. See if you confirm.